Is Natalie Behague, who's a postdoc at the University of Victoria. So she has woken up at 6 a.m. Pacific time to join us today, and she's going to speak to us about synchronizing times for K-sets in Automata.
Thank you, and thank you very much for inviting me to speak. So this talk is about synchronizing times for K-sets in Automata. I'll explain all of these words. And I should say this is all joint work with Robert Johnson, who is at Queen Mary University of London. Okay, so first of all, what's an automaton? An automaton is very simple. It's just a set of states. We usually label them 1 up to n, and a collection of mappings, finite set of mappings from the set of states to itself. So in this picture I've drawn, this automaton has 4 states, 1, 2, 3, and 4, and it has 2 mappings, F and G, and you can see that F takes 1 to 2, 2 to 3, 3 to 4, 4 to 1, and G takes 1 to 2, and everything else gets sent to itself. Okay, so an automaton is just some states and a set of mappings. And what we're going to care about in terms of automata are words, which are sequences of mappings and how they act on the set of states. So we're allowed to take sequences of the mappings and apply those to the sets of states, and we're interested in how those words act on the set of states. And in particular, we care about a reset word, which is a word that sends every state to the same state. So in this particular example, if you look at what the word G, F, 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 G, F, 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 G does, you can check that that will send every single state to the state 2. So if we follow what state 1 does, it goes to state 2, then it goes back round to state 1, then it goes to state 2 again, then it goes back round to state 1, and then it goes to state 2. So it ends up in state 2 if you follow G, F, 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 G, F, 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 G. And the same, if you try it with any of the other states, you'll find that the same thing happens. They'll end up at 2 at the end. So this particular word sends every state to the state 2, and therefore is a reset word. And a synchronizing automaton, which is one of the words, well, synchronizing automaton wasn't one of the words in the title, but synchronizing was, is just an automaton that has one of these reset words. So this particular example is a synchronizing automaton because the word GFFFGFFFG was as a reset word. Not every automaton is going to be synchronizing, because if both of your mappings were just a permutation of the set of states, you're never going to get a reset word, for example, because any word is just a permutation. Then no word's going to send every state to the same state. Okay, so these are very important definitions. So if you have any questions at the moment, you should definitely ask them, or we will move on. Okay, so the big open conjecture in the land of finite state automata is Cherney's conjecture. So Cherney conjectured that if an automaton has a reset word, so if an automaton is synchronizing, then it has a reset word of length a length at most n-1 squared. So going back to our example from before, this wasn't just a randomly chosen example. It was actually sometimes called Cherney's automaton or the standard automaton. This automaton has 4 states, so n is 4 here, and I told you last time that we had a synchronizing word, GFFFGFFFG, and you can see that has as a length 9. It's got 9 letters, and that's the same as 4 minus 1 squared. So that shows that it's best that the conjecture would be best possible in the case of n equals 4, but actually a very simple generalization of this automaton. So taking n states and 2 mappings, one which is a circular mapping, sends every state to the next state, and one which is analogous to G and sends everything to itself except from 1 gets sent to 2. If you analyze that automaton in general, that would achieve its synchronizing, but its shortest reset word as length n-1 squared. So that's where the conjecture comes from. It's by a conjecture that basically this is the worst case example, that any other automaton with a reset word has a reset word of length at most the length that this automaton has. Okay, so very big open conjecture. Some progress has been made towards the conjecture. I'll tell you first of all about some trivial upper bounds that we can find on the reset word length. So the very first simple argument is if you consider just a pair of states, how long would it take to send that pair of states to find how long would a reset word be that sent that pair of states to a single state? So sent them both to the same state. Well, if you think about how a word acts on that pair of states, it's going to send that pair to another pair, to another pair, to another pair, until eventually they both get sent to the same state. They both get sent to a singleton. And how long could the shortest such word be? Well, worst case scenario, your pair of states has to pass through every single other pair of states before you can map it down to a singleton. So even the worst case pair of states only takes n choose 2 steps to get mapped down to a singleton, because you just maybe have to pass through every single other pair before you get down to a singleton. So this gives us a very naive upper bound where we just pick a pair and find a word that maps that pair to a singleton of length n choose 2, and then we pick a pair in the image of that word and we map that pair down to a singleton, and we concatenate the words, and so on and so on. So if we do this, eventually we'll get everything mapped down to a singleton, a single state, and the reset word that we found will have length at most n-1 times n choose 2. Okay, so that feels like the argument has a lot of slack, because at no point were we attempting to find the best pair in the image that would have the shortest mapping down. We were just saying, oh, we'll take any pair, and at worst it has n choose 2 time steps to n choose 2 letters to get mapped down to a single state. So there is a better upper bound. This was found by Frankel and Pin in 1983. And the idea behind their upper bound is that they basically take this simple bound and they improve it by saying, if we started with k states, we can find a shorter word sending some pair within that k states to a singleton. So in fact, they've shown that if you have k states, you can find a word of length at most n-k plus 2 choose 2 that sends that set of k states down to a smaller set of states. So in particular, some pair in that set of k states has been sent to a singleton. And if you repeatedly apply this, you just start with n states and then go down to a smaller set and then to a smaller set and so on. You sum up these values that you get from this Frankel-Pin theorem, and a corollary is that you can find a reset word of length n cubed minus n over 6. That's just summing these binomial coefficients. So that's better than our naive upper bound, which was like n cubed over 2. This is like n cubed over 6. But it's still quite far from the actual conjecture, which was n squared. So it's definitely an improvement, but it's only a constant improvement. Okay, so that was in 1983. So what progress has been made since 1983 on going from n cubed over 6 to n squared? Well, actually, turns out it's quite hard to make progress on improving this constant. So the very best known bound at the moment, actually I think this might be slightly out of date. I think there might be a slightly better one since, but it's basically like a tiny epsilon improvement in this factor of 1 over 6. So the best known bound, which took quite a lot of work, different papers contributed to this, is 0.1654 n cubed, whereas obviously 1 over 6 is 0.166 n cubed. So very, very small improvement, especially given that the actual conjecture is that it's more like n squared and not like n cubed at all. Okay, so that's the state of the art of Charlie's conjecture. That hopefully that's convinced you that it seems quite simple, but actually turns out to be very difficult to prove anything about. Okay, so there are some cases where the conjecture has been proved, some special classes of automata where it's been proved. So I'll just mention some of these briefly. If your automaton is orientable, which is just a special class of automata, and it was proved by Epstein. Every automata has an underlying directed graph where you just sort of remove the labels from the mappings and you just think of them as directed edges. If that directed graph is Eulerian, turns out then the conjecture holds. It's proved by Carey in 2003. Another case is if one transition function is a cyclic permutation of all of the states, then, one of the mappings, I changed my terminology, but one of the mappings is a cyclic permutation of all the states, then that's also, then the conjecture is also true in that case. You'll notice, I didn't tell you what orientable means, but for the other two that I did tell you what they mean. In all of these cases, the standard automata or Chinese automata that we talked about before is something in each of these classes. So they've sort of tried to generalize the automata that we do know about, the standard automata, and find classes where we can prove the conjecture. But in general, it remains wide open. Okay. So let's think about it a bit more. Let's draw a picture of the power automaton, which is a very natural thing to consider. So I'm going back to my favorite automata, this 4-state standard automaton. And its power automaton is formed by, we take a new automaton where each state is a set of states from our original automaton, and we draw the mappings as to how that mapping acted on that set of states in the original automaton. So, for example, if we take the set of all states 1, 2, 3, 4, F is just a permutation on these. So F sends the set 1, 2, 3, 4 to the set 1, 2, 3, 4. So draw that little loop up there. And G sends the sets 1, 2, 3, 4, the set of states 1, 2, 3, 4 to the states 2, 3, 4. So we draw this arrow going from 1, 2, 3, 4 to 2, 3, 4. So this is a very natural object to consider, because in terms of Chinese conjecture, we're always just talking about how short is a word that sends everything down to a singleton. So in terms of this picture, a reset word is a path that takes you from the set of all states 1, 2, 3, 4 down to one of the singletons. So in this picture, it's a lot easier to see that GFFFGFFFG is a reset word. If you just follow those labels, GFFFG, FFFG, then you'll see that takes you from 1, 2, 3, 4 down to the state 2. So it's much easier to see in this picture that applying that word takes every state to the state 2. And in terms of the other things we've talked about, say the Frankel-Pin theorem, the Frankel-Pin theorem tells us that given any set of k states, we can find a word of length n minus k plus 2, choose 2, from that set to the next layer down in this picture. So I've layered the picture where the sets of states are grouped according to how many states they have, and the Frankel-Pin theorem is telling us that we can, for anything in say layer 3, where we have 3 states, we can find a word that's not too long that takes us down to layer 2. By not too long in that case would mean n minus 1 choose 2. 3 choose 2. Okay, so in terms of this picture, I said that proving Chinese conjecture is like finding the shortest path from the top layer to the bottom layer. What if instead of aiming for the ground heights of Chinese conjecture, we asked about something else? What if we instead said, okay, we can't prove what's the shortest path from the top layer to the bottom layer. Can we prove what the shortest path is from, say, the third layer to the bottom layer? What if we asked just for that instead? From the third layer to the bottom layer for a general automata, can we prove a bound on the shortest path there? So just to get your bearings here, when I say the shortest path, I mean I get to pick the best state in a layer and find the shortest path down to the singletons. So the shortest path from the second layer to the singletons is always going to be a path of length 1, because there's always just a pair that maps down to a singleton in one move, unless you're not synchronizing at all, but if you are synchronizing, you have to have some pair that maps to a singleton. And in this case, in this example, the shortest path from a set of 3 states to a singleton, you can check is doing G, F, 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 G, and that's 5 moves. Okay. So with that question in mind, we define the k-set rendezvous time to be the length of the shortest path from the kth layer to the singletons layer. So that's, in terms of words, it's saying we can find a set of k states and a word of length at most this rendezvous time that sends that set of k states to a single state. Okay, so what's known about this k-set rendezvous time? Well, there are some lower bounds. The standard example tells us that the rendezvous time for k is at least k minus 2n plus 1. And Gonzo and Jungers, who worked on this and introduced in particular the triple rendezvous time, focusing on going from the 3rd layer to the singletons, actually showed that in that case, the standard example isn't a tight lower bound, which is kind of surprising because we conjecture that it is a tight lower bound for the Cherney's conjecture. But at least in the case of going from the triples to the singletons, it's not tight, and they have a particular construction of an automaton where the best triple has a path of length n plus 3 to a singleton, whereas in the standard automaton, every triple has a path of length at most. There is a triple that has a path of length at most. That has a path of length n plus 1 to a singleton. So in their construction, it takes 2 more steps to get from a triple to a singleton. Okay, but what we're really interested in is upper bounds, of course, because everything to do with Cherney's conjecture is about trying to prove upper bounds on the shortest reset word. So we want to prove upper bounds on this k-set rendezvous time. So what can we prove about the k-set rendezvous time? Well, if we just apply the Frankel-Pin theorem, if you remember from before, that's a theorem that tells us worst case scenario going from the kth layer to the k minus 1th layer, and so on. So we can say this bound comes from saying we can go from the kth layer to the k minus 1th layer in one step if we pick something in the kth layer that immediately has a mapping down to the k minus 1th layer. But then going from the k minus 1th layer and so on, we just assume maybe we were in the worst case scenario from that point onwards. So maybe it takes the worst case number of steps according to the Frankel-Pin theorem to get from that layer to the next one down, and we just sum those up. And the bound that gives you, just doing that sort of direct application of this theorem, is k minus 2 over 2 times n squared is an upper bound on the rendezvous time. And Gonzo and Jungers, who I said specifically looked at triple rendezvous time, found a better upper bound on the triple rendezvous time of 0.1545 n squared. That's not a precise constant. They sorry, going too fast. That's an approximation of their constant. So yes, so those are some trivial upper bounds. Well, so the Frankel-Pin theorem is a sort of trivial if you already know Frankel-Pin, and the Gonzo and Jungers one is very not trivial. They proved it using linear programming and methods associated with linear programming. Okay, so what have we done in terms of this k-set rendezvous time? Well, first of all, we've proved a general theorem, which has a very nice and simple proof, actually, that's an improvement on the upper bound for the k-set rendezvous time in general. So if I haven't kept it on this slide, but the Frankel-Pin bound was k minus 2 over 2 times n squared. This bound is more like k minus 1 over 4, at least if k is odd, times n squared. So it's a factor of 2 improvement on the sort of trivial, not trivial, but the standard application of the Frankel-Pin theorem. And we also worked on some small values of k to try and improve the upper bound for those. So we haven't found improvement on Gonza and Junger's result for the triple rendezvous time, triple rendezvous number. We have 0.191 n squared, which is a bit bigger than their constant. But our approach to proving this is purely combinatorial, doesn't involve linear programs. And in particular, we can generalize it to at least 4 sets and 5 sets. We have these improved upper bounds for 4 sets and 5 sets. So if you compare these, what this theorem 1 would give you when k equals 4 is n squared over 2. So this is an improvement on that n squared over 2, is 0.459. And in the case of k equals 5, our upper bound is just n squared. So it's 0.798 is actually quite a lot of an improvement on the constant 1 n squared for k equals 5. So, yeah, our approach was purely combinatorial, no linear programming. And so we remain hopeful that the approaches could be generalized to try and get maybe more general, better upper bounds for k, or at least so these approaches could be tweaked to get better upper bounds for these small cases. And the dream is that understanding this k-set rendezvous time actually leads to an understanding of Cherney's conjecture itself. A sort of taste a baby example. If you could prove something about these, maybe you could prove something about Cherney's conjecture. Okay, so what time are we on? Oh, we have loads of time. So I'm going to talk a bit about the proofs of both of these theorems. And we'll start with the proof of theorem 1. So here's the statement of the theorem, just to remind you what we're aiming for. And how does the proof work? I'll just sketch it in a particular example. So let's just take k equals 6. So we want to find a shortest word from a set of 6 states to a single state. The idea behind the proof is not particularly complicated, actually. So the idea is you just apply Frankel-Pin, but you apply it more cleverly than just going from the set of k states to k-1 states in one move, and then assuming you've got the worst case scenario from then on out. So what we're actually going to do in this case k equals 6, we know we can find a word from a set of n states, a set of n minus 3 states, that takes at most 1 plus 3 plus 6 steps. So we can go from n to n minus 1 in one step, n minus 1 to n minus 2 in at most 3 steps, and n minus 2 to n minus 3 in at most 6 steps. That's just applying Frankel-Pin in those cases. And we also know that we have confined a word from any triple to a singleton in at most n minus 1 choose 2 plus n choose 2 steps. Again, just applying Frankel-Pin directly. So how do we put these two things together? What we say is that to find a map from a set of 6 states to a singleton, we have a word that takes the set of n states to a set of n minus 3 states. So in particular, we must be able to find 6 states within that, 6 states within all of the states, that get sent to only 3 states under the application of that word of length 10. So we observe that word of length 10, and we find some set of 6 states that send that word of length 10 sends to only 3 states. And then we apply the second thing, and we'll get, we can go from that set of 3 states to a singleton at most n minus 1 choose 2 plus n choose 2 steps. So that's just how we get this improvement, is you, rather than looking at going from sort of the kth layer down, you go from the nth layer to the n minus k over 2th layer in sort of this very small number of steps. And then you find some set of k state that word sends down to a set of roughly k over 2 states. And then you just apply Frankel-Pin to that k over 2 states and send that one layer down at a time to a singleton. So in general, you'll get this sum at the bottom where that is exactly doing this process, but more generally. Okay, so that's as you can see, not a super difficult proof. It's kind of surprising that it's not been observed before. It's just a half factor improvement on the Frankel pin, on the trivial Frankel pin upper bound, just by a slightly more clever application of Frankel pin. Unfortunately, if you substitute in k equals 3, this isn't actually an improvement on the naive Frankel pin bound, because you sort of lose something from this floor function. So in the case of k equals 3, we still get that the rendezvous time is at most n squared over 2 from this argument, and just applying Frankel pin directly also gives you n squared over 2 roughly. So we would like something better in the case that k equals 3 at least. Okay, so that brings us on to theorem 2, and I'm not going to prove the case. I'm not going to sketch for you the cases of k equals 4 and k equals 5, even though those are where we made our improvements over Gonzer and Junger's, because the case k equals 3 basically captures everything that we then generalized to k equals 4 and k equals 5. It's not entirely true. Generalizing to k equals 4 and k equals 5 from k equals 3 requires some care in the iteration, and not just saying, oh, we'll just do it twice. So you have to be a bit more careful than that. But all of the key ideas behind it are in the k equals 3 case. So it's not super illuminating to do the k equals 4 and k equals 5 cases once you've seen how the k equals 3 case works. So, and the k equals 3 case is a little bit more straightforward as well. So I'll just sketch how to prove the k equals 3 case, and then you can go away and imagine that the k equals 4 case and the k equals 5 case are, you just sort of iterate that in a slightly clever way. Okay, so here's our goal. We want to prove this upper bound on the rendezvous time, the triple rendezvous time. So what does that mean? It means we want to find a word, we want to find a set of 3 states, a triple, we want to find a word, sends that triple to a singleton, and that word has a small length. Okay, so the idea behind this proof is we start by defining a rank of a word, which is just the number of points in the image of the word. And we let R be the minimum rank over all words of length at most n. It'll become a little bit clearer later, hopefully, why we've chosen to do this. But the idea is, if we let R be this minimum rank over all words of length at most n, we can write down 2 claims. The first claim is the claim we sort of want to use when R is very small. So that means there is a word of length at most n which has a small number of points in its image. And in that case, it probably makes sense to you. We have a word that's of length at most n. That word doesn't have very many points in its image. So it seems logical that we could probably use that to get claim 1, where that this n here is you just take the word W itself that has small rank, and then you look at its image and you somehow send that down to a singleton, and you get claim 1. So in the case that R is small, we get that we can find this n plus r plus 2 choose 2 length word sending a triple to a singleton. And the slightly more surprising case is when R is quite large, where you can also find a decent upper bound on the minimum length word sending a triple to a singleton. So that means that every word of length at most n has quite a lot of points in its image. And that turns out to be useful. You can think of that as saying, no matter which word we take, there is always, from say a triple to a pair, there's always going to be quite a lot of things in its image, in the image of that word. And it's not immediately obvious why that's helpful, in the same way that it seemed to be helpful when R was small, but it is, in fact. So we proved these 2 claims, and then the idea is just to take a minimum over the two upper bounds. So let's just sketch how claim 1 works. So remember, we're trying to find this upper bound n plus r plus 2 choose 2, where r is this, I've written it in sort of slightly confusing notation, but it's just the minimum rank over all words of length at most n. So in this case, we're assuming, we're kind of thinking of r as being quite small, so we're going to fix some word that has this small rank. Fix some word of length at most n that has this small rank. And consider the set of points with two pre-images under this word. So here's a sketch of what the image of this what this set of states looks like, and how W acts. So this picture is supposed to show that everything in A had two things in its pre-image under W. So two things get sent to everything in A. Everything in B has just one thing that gets mapped into it under the word W, and everything in C is not in the image of W. So these are all states that don't lie in the image of W. So from this picture, we can deduce that. So we know that the size of n is all of the set of states, A plus B plus C, but we also know that n, which is the total number of states, is twice A plus B, because it's that if you look at the pre-images, everything gets sent to something, and you can see that. Oh, I should say at this point, if anything under W, if W itself sent a triple to a singleton, then we would already be done. We'd already found a word of length n, most n, that sent a triple to a singleton. So we can assume that it only sends pairs to singletons and never triples. Okay, we also know that W has rank R, so that means it only has R things in its image. So we know that C has size n minus R, and from this equality here, we know that the size of A is the same as the size of C, so A also has size n minus R. And then to finish off the proof of the claim, we just apply Frankel-Pin to the set A. So what we have here, we apply W to send some pairs to some singletons, and then we can find one of the pairs within A that gets sent to a singleton. Frankel-Pin will tell us that if the size of A is n minus R, then some pair within it gets sent to a singleton in R plus 2 choose 2, at most R plus 2 choose 2 steps, in a word of length, most R plus 2 choose 2. So we apply the word W, and then we apply that word that sends some pair in A to a singleton. And actually, we've done better than find something sending a triple to a singleton. We found something that actually sends 4 states to a singleton. So everything in A had 2 pre-images under W, so we're going to have 4 things getting sent into A, and then that pair in A is going to get sent to a singleton, and that whole process, applying W and then the word sending a pair to a singleton, has length at most n plus R plus 2 choose 2. Okay, so that was the proof of the first claim. We can also prove our second claim roughly in a sketch. Oh yeah, and I sort of said that at the end. Okay, so claim 2 is when we're thinking about R instead being quite large. So this says there exists a word that sends a triple to a singleton, and its length is at most n plus n minus R times n over 2. And again, R is this minimum rank over all words of length at most n. And it's in claim 2 where we actually use the fact that R is this minimum rank over all words of length n. Because in claim 1, we just used that there was some word that had small rank and not too much length. Okay, so how are we going to use this? Here we're thinking of R being quite big, and we know that every word of length at most n has quite big rank, has quite a lot of states in its image. So, okay, so first of all, slightly technical condition. We assume that the automaton is strongly connected, so that just means that for every state, and so every state x and every state y, there is some word that sends x to y. And it's safe to assume that it's strongly connected, because if you have an automaton that's not strongly connected, you can reduce it to a strongly connected one by just looking at all the states that do send to each other, sort of the sync states, we call them sometimes. Okay, so we're just going to assume it's strongly connected. That's a slightly technical condition that basically means that we can find a word sending any state to any other state. And we're going to define a good pair to be a pair that can be reached from a triple in at most n steps. So these are pairs that are quite easily reached from the set of triples. So here's my picture. First of all, note that I can find some mapping F that sends some pair to a singleton. I have a synchronizing automaton. There must be some mapping that sends at least a pair to a singleton. If it sends a triple to a singleton, then I'm instantly done. So it sends at most a pair to a singleton, maybe several pairs to several singletons, but at least some pair to some singleton. So call that singleton X. So this is the image of, this is my picture, this is the image of F. Everything in this blob is in the image of F. Everything in this other blob is not in the image of F. And in particular, we have some state X that two things got sent to it under the application of F. And so how many good pairs is X in? Well, if you take X and any other state that's in the image of F, that's definitely a good pair. That can in fact be reached from a triple in one step, right? So if you think of the pre-image of that pair, X and something else in the image of F, if you take the pre-image from F, then you get a triple. So that pair can be reached in one step. So that's a good pair. And how many good pairs is X contained in? Well, it's just the size of the image of F, which we know is at least R. We're thinking of R as being quite large. So we know that there are quite a lot of good pairs that can be reached in just one step, just by looking at the image of F. And then we use our strongly connected. So we use our strongly connected and we say we can find for any other state of the automaton, we can find some word. And in fact, that word will be of length at most n because it's a shortest path from one state to another. So you can find some word, actually, length at most n minus 1 even. So you can find some word of length at most n minus 1 that sends X to any other state. So pick some other state Y. We have some word sending X to Y of length at most n minus 1. So in particular, if you think about the word F concatenated with that word sending X to Y, that's going to send some pair to Y. And that's also itself a word of length at most n, so it's got to have rank at least R. So just applying that same argument that we did to the image of F to the image of this new word, we can see that any state Y is also going to be in at least R good pairs. R minus 1 good pairs, I guess, because you can't count Y with itself. So from the argument, just to repeat, we can find some word for any state Y. We can find some word of length at most n that sends a pair to that state Y. We look at the image of that word, and we can see that taking Y with any other state that's in the image of that word, gives us a good pair. And we also know that word has rank at least R, so that tells us there are at least R minus 1 good pairs containing that state Y. And that's true for every state of the automaton. So if we sum all of those up, every state is in at least R minus 1 good pairs. We might have double counted because we may have counted, say, pair XY and YX twice. So we know that there are at least R minus 1 times n over 2 good pairs. Okay, so how do we then use this? So that means we have lots and lots and lots of pairs. We're thinking of R as being quite large here. We have lots and lots of good pairs, which can be reached from a triple in at most n steps. So now, in contrast, to find a bad pair to be some triple that can't be reached in at most n steps, how many bad pairs are there? Well, there's n choose 2 minus the number of good pairs. So there's going to be, if you calculate that, it's quite a simple calculation, it's just n minus r times n over 2 bad pairs. Now, where have you seen n minus r times n over 2 before? It's in the statement of the claim. So there are most n minus r times n over 2 bad pairs. And now we finish it off. Pick the good pair with the shortest path to a singleton. Worst case scenario, it might have to pass through every single bad pair before we can reach a singleton. So worst case scenario, that good pair, the word that sends that to a singleton, the minimum word that sends that to a singleton might have length n minus r times n over 2. So we put that together, we have some word that sends a triple to that good pair in at most n steps, and then some other word that sends that good pair to a singleton in at most n minus r times n over 2 steps. And that's where this bound comes from. Just sum those two things. Okay, so now to finish the proof, we just put those two claims together. We find some word sending a triple to this of a singleton of length at most, the minimum of n plus r plus 2 choose 2 and n plus n minus r times n over 2. The first is increasing with r and the second is decreasing with r. So worst case for this minimum is when those two things are actually equal. So we can just set r plus 2 choose 2 equals n minus r times n over 2, solve that quadratic in r. And you get worst case is when r is about minus 1 plus root 5 over 2 times n. So that's where our mysterious constant came from at the start that had square roots in it. It's just solving a quadratic in r. Okay, so if you do the calculations, very simple calculations, you get that the rendezvous time is at most 3 minus root 5 over 4 n squared plus 3 over 2n. So 3 over 2n is a less important factor. So as you can see, that proof was entirely combinatorial, all very elementary, and I haven't explicitly told you how to generalize it to 4 and 5, but I mean, I can tell you a bit in words. So claim 1 actually translates directly to k equals 4 case, right? Because actually in claim 1 we observed when we proved it that we were finding actually something that sent a word that sent a 4 tuple to a singleton. So claim 1 was a bit overpowered, really. And then the analogous thing to claim 2 in the case that k equals 4 will just be you sort of iterate that process twice. Sorry, excuse me. And that's how you find the bound for k equals 4. And again, similarly for k equals 5, you sort of just generalize these ideas as much as possible. And you can continue generalizing these ideas beyond 5, but the reason I haven't written those bounds down is because the bounds that you get if you keep generalizing the ideas beyond 5 are not actually any better than the bounds we get from theorem 1, that floor function of k minus 1 over 2 n squared over 2. So these ideas are helpful in the k equals 3, k equals 4, k equals 5 case to improve on theorem 1, but actually theorem 1 is the stronger theorem for k equals 6 and above. So generalizing these ideas isn't enough to improve on theorem 1, which is a bit surprising. And basically the weakness is, at least what I think the weakness is we have, in k equals 3, the gap between these two things, we have an r plus 2 choose 2 term and n minus r n over 2 term. They're both, I don't know, they both feel quite quadratic, and you can get some reasonable bound out of them. But as you start increasing k, it feels like you're really only dealing with the edge cases. You can deal with the case when this rank is very small, and you can deal with the case when this rank is very large, but all of the stuff in the middle where the rank is some sort of middling value, we don't have a corresponding claim 3 that deals with or even claim 3, 4, 5, that deal with sort of middling values of rank quite successfully. So the sort of peak, when you take the worst case scenario, is going to be some middling value of R, and these bounds are just not strong enough to help, really. So my feeling is that if you wanted to improve on these, at least improve on these methods directly, you would want to find some extra claim or some strong improvement of, say, claim 1, which feels like it has quite a lot of slack in it, that works quite well when R is one of these sort of middling linear and n values. So there's definitely, it feels like there's space where this could be improved, but actually improving it has proved difficult. Okay. So I have 10 minutes left, so I'll elaborate a bit some more on my open question. So I've just talked a little bit about my first open question, which is, can these methods be generalized for k greater than 5? So as I said, they can, I mean, you can directly generalize them, but they don't give you anything better than Theorem 1 in their current form. So maybe we need some better ideas. We need some extra claims, or just need to add something onto it to deal with that middle case. But we have a much even stronger conjecture, which I've stated in the case that k equals 3, but I'm suspicious. I'm not going to be bold enough to say as a conjecture, maybe as a question, but even when k is some fixed constant and n is large compared to k, I think this may hold. But we'll state it for the case k equals 3. The conjecture is that there exists some constant such that the triple rendezvous time is actually constant in n. So you'll remember that a lower bound on the triple rendezvous time was n plus 3. And you'll also recall that the best known upper bound on the triple rendezvous time was due to Gonzer and Jungers, and it was like 0.15 n squared. And we can't find any examples better than this lower bound of n plus 3, despite searching. And it also feels like both our upper bound and Gonzer and Jungers' upper bound, it feels, at least to me, like there was more slack there than there was in trying to find any counterexamples. So it's a conjecture, may or may not be true, but the conjecture is that, in fact, the triple rendezvous time is linear in n. And the hope is that the hope is that any proof of this, while I guess it wouldn't directly lead you to a better upper bound for Cheney's conjecture, it might well in methods and ideas lead you to get somewhere close to Cheney's conjecture. Maybe proving this for triples would allow you to prove it for all fixed k, and that would be a pretty good thing to do. So yeah, so I've just told you the whole talk telling you that we've managed to improve the triple rendezvous time, and the k-set rendezvous time is some smaller constant times n squared. But just like with Cheney's conjecture, I think that the actual conjecture value is a whole factor of n better than our constant times n squared bounds. But just like Cheney's conjecture, it might be difficult to actually reach it. Who knows? Okay, so the final open question I wanted to mention is the worst triple. So we've been talking all this time about we get to pick something in the kth layer, the best thing, and find its shortest path down to a singleton. The Frankel-Pin theorem is more along the lines of the worst triple. So the Frankel-Pin theorem tells you if you take any k-set, then it might take quite a long time to get sent to a k-1 set. So we can ask that question. I've asked it here just for triples, but you could ask it for any k. What is the worst case scenario of how long is the shortest word from the worst triple to a singleton? So worst means it has the longest, shortest word. So it just basically means if you pick any triple, you're finding a bound on its shortest word sending that triple to a singleton. So the question is there some constant such that for any triple, some constant less than 1 such that for any triple there is a word from that triple to a singleton of length most that constant times n squared. So I've specified that from this question we want the constant to be less than 1, because just applying Frankel-Pin twice would give you a constant of 1 here. So applying Frankel-Pin tells you can go from a triple to a pair in like n plus 1 choose 2 steps, and from a pair to a singleton in like n choose 2, from a triple to a pair in n minus 1 choose 2 steps, from a pair to a singleton in n choose 2 steps, and that is like n squared steps. So if you could, considering now the worst triple, find some better constant times 1, this would actually, any improvement on that constant would actually, you could instantly ramp it up to get an improvement on the Frankel-Pin bound, at least improvement on the n cubed over 6 to Cherney's conjecture. And it depends on how much smaller your constant is as to whether it improves the state of the art bound for Cherney's conjecture. I guess if it was only 1 minus some very small epsilon, you might not improve this 0.1654 state of the art Cherney's conjecture bound, but you would certainly improve the n cubed over 6. And why would that be true? Well, you basically, if you know that you can go from a triple to a singleton in length at most cn squared steps, then you can just go from the set of all states to the singletons by going through 2 layers at once. And I won't go into all of the details, but you can basically think of it as the Frankel-Pin bound is going from 1 layer down to the next layer, down to the next layer, 1 layer at a time. Having a positive answer to this question you could generalize the Frankel-Pin theorem to something saying we can go down 2 layers at a time. So we go from n to n minus 2 and n minus 2 to n minus 4 states. And every time we do it, it takes some smaller constant than 1 times n squared steps. And summing all of those up, you would get instantly something better than 1 over 6. So both of these questions I think are interesting. I think that the second question is obviously interesting because it would immediately give you an improvement to the bounds for Cherney's conjecture. But I think that the first question is it wouldn't instantly give you a bound improvement to Cherney's conjecture, just like the second question, but it's like in miniature captures the difficulty we have for the hold of Cherney's conjecture, where all we can prove is that it's like constant times n squared, but we think the true value is actually constant times n. Where if you compare that to Cherney's conjecture, all we can prove is that it's like some constant times n cubed, but we think the true value is actually like n squared. So I think that nailing down this first conjecture might actually be really helpful in nailing down some ideas for Cherney's conjecture itself, potentially. And I think I will stop there. Thank you very much.
Oh, thank you so much. Does anyone have any questions for Natalie? Misha, did you have a question?
No, just wanted to say that I very much like this nice talk.
Thank you.
Maybe I have a question.
Oh, yeah, go ahead.
Okay, I'll first start my video. So thanks for the talk. So my question is on this last open problem. If you would know if you would have a constant c less than 1, can you tell me what would be the improvement in the Frankel-Pin bound? Would it just be multiplication by c?
I think so. I think so. Yeah. I think so.
Okay, yeah, that would also be my guess, but I was not completely sure. Thank you.
So do you think it's worth sort of going up to larger and larger Ks to try and get similar bounds? Is that helpful to keep going past, 5 or 6 or?
Well, I think the real meat of the question is actually, so my suspicion is that if you could just for one fixed K find that it was linear. So I've put K equals 3, but maybe there's some difficult K equals 3 and you could do it for some other fixed K, I don't know. But that would be much, much better, finding that that was linear than sort of finding slight improvements of the constants for larger and larger K, probably. So yes and no, but yeah, I think that we tried to just generalize our work naively because why not? And it turned out to not be. But I think trying to just find slight improvements in the constants for larger and larger K wouldn't be interesting in and of itself. If you found some quite big improvements, maybe. And if you found like some general theorem that was an improvement in the constants for all K, that would also be interesting. But I think the real interesting question is it actually like n squared or is it more like n? So if you could, maybe the conjecture's false, maybe you could improve on the lower bound. I think, and that would be very interesting too. So yeah, fiddling around with the constants, not the most interesting part, but maybe it's all we can achieve. It's all we've been able to achieve for like 40 years with Journey's conjecture itself is fiddling with the constants. So yeah.
Can I ask how you got into this Czerny stuff?
It was Robert Johnson actually who found the problem. So he'd heard it's very big in computer science, of course, and he'd heard lots of people being interested in it, and also some lots of group theorists have thought about it, and he felt it had been underexplored from a combinatorial perspective because it is kind of a combinatorial question. You can think of it in terms of these pictures of sort of like a bit like directed graphs. And so he wondered if bringing a combinatorial viewpoint onto it might yield some fruit. So all the credit for finding the question really goes to Robert Johnson. But yeah, it's a big question in computer science. It's been thought about by algebraists. It hasn't really permeated into the combinatorics community very far, I guess. So maybe there's more room for some combinatorial tools to be applied.
Great. Yeah, once again, does anyone have anything else? If not, thanks again, Natalie.
Thank you.
For